In this session, I'm going to discuss on another machine learning model, which is support vector machines. So it's a supervised machine learning algorithm. It separates data using hyperplanes. Okay. So how we are going to divide this is, so wherever the classes are there are two classes. We draw a support vector, and then once we have a support vector we will draw an hyperplane in between that in such a way that the distance between AC is equal to CB. Okay, so this here is the hyperplane and these two are the support vector. This is class belongs to A. Let's say A class, and this is B class. Okay, so let me explain this completely. So different classes are separated by two lines known as support vectors. Okay, this this is one class and this is separated by support vector, and this is another class which is separated by a support vector. Okay, and the line that runs between them is known as hyperplane. So this is the hyperplane that runs in between them, or runs between them is known as hyperplane. The support vectors are positioned on the edge of the class. You could see that this is the edge over here, right? So we have the support vector which is positioned exactly at the edge of the classes in which they each lie. Okay, so support vector machine works well on multi-dimensional sets as well. Okay, so now let's see the theory. So the line passing through first class and the parallel line for second class. So this is support vector. Okay, the line passing through first class and the parallel line for the second class is the support vector. So now let's see the hyperplane, a line passing in between the two support vectors. So it's passing in between the support vectors and dividing it into equal parts, two equal parts. Okay. So dividing it into two equal parts, and these parts are known as margin. So this is known as margin, one margin, this is another margin, and they are equidistant. Okay. Our main aim is to consider the highest margin. Okay, so we try to consider highest margin because throughout our classification we want our classification to be properly defined. Okay, because of that, so that we have a proper classification, that's why we need to have highest margin. That is our aim. Okay, so let's take an example. Okay, imagine a village where two brothers are fighting for a piece of land and comes to you for a solution. What solution would you give? Yes, you will try to divide it into two equal parts. Similarly, here the hyperplane over here tries to divide into two equal parts. Okay, so this is the notes I have prepared. So in brief, we can say support vector machine is a supervised machine learning algorithm, and it separates data using hyperplanes. So hyperplanes can be one-dimensional, a point. Okay, in one-dimensional we have a point as an hyperplane. In two-dimensional we can have a line. Okay, the line will divide it in equal parts in two dimension. In three dimension we need a plane to divide equally in divide the class equally, and in four dimensional we are using the hyperplane. Okay, so now let's see the same example. So support vector machine. Let's say we have a group of rabbit and lion. Okay, the class belongs to rabbit and class belongs to lion. So what we have to do is that first we have to draw support vector parallel to rabbit and lion at the edge of the classes. Okay, so we have a rabbit class. We are drawing a support vector at the edge of the rabbit class, and then we are drawing another support vector at the edge of lion class. Now, what we have to do is that we have to draw an hyperplane which is equidistant from the two support vectors. Okay, this hyperplane that we have drawn, which is equidistant. Okay, this is the decision boundary that we got, and this is the margin. The distance between the hyperplane and the support vector from both sides, that's the margin, and it is equal. So this is all we have discussed till now. Okay. Now, so now let's say, why do we draw a margin like this? Why can't we draw a margin like this? Okay. So the problem here, why can't we draw a support vector and hyperplane like this? The problem is that here, if you see, we have try to cover a larger margin. Okay, so we are getting a larger margin, and also hyperplane and support vector are in such a way that they are trying to give us the maximum margin as possible. But if you see here, if we draw a parallel lines like this, you could see we have a very less margin, right? So this support vector that we have that are close to each other, and also it's close to hyperplane also, which is not a good thing actually. So our decision boundary should be in such a way that is having a maximum margin as possible from the support vector, some from the support. So this is our goal. Okay. So now let's come to kernel trick. Okay. Kernel trick, it allows us to operate in original space without capturing the data into higher space. So it's nothing but we will capture our data points or operate in original space rather than capturing the data into higher space. That's our main goal. Let's say I have some classes as shown in the below diagram, which is not separable. If you see here, we have two classes, red class I will call and green class. So you have to do this separation. Okay, how are we going to separate this red class from blue green class? So we have to make sure that we have to do separation in such a way that we get one red class in red class and green class separated. Okay, so what we will do is that this is a one dimensional. Okay, how can we separate it with just one dimension? Hence, we have to go into higher dimension. So what we'll do, we use a transformation technique and go to a higher dimension. So we have phi of x is, so this is x, right? So I will take x mod 2, okay? So let's call this as point 0, 1, 2, 3, 4, 5, 6. So x mod 2 will give, so if this is 0, green, so 0 will go x mod to 0, it will give remainder 0. And the 1 will give remainder x1 mod to 1. Okay, here it will give. So 2 mod to 0, it will come here. 3 mod to 1, it will give, go up. Okay, like that it will happen. So in such a way that after the transformation of all values, it will separate all the classes which we have. Okay, so let's see all the red values go up and all the green values come down. So we are able to separate the two classes when we move to one higher dimension in this case. Okay, so by using the transformation technique, as you can see that the point were not separable in one dimension. Yes, we can see. So which was the original dimension, but after applying the transformation, it become linearly. So once we made the transformation, it has become linearly separable like this. So we keep on increasing the dimension unless the classes are separate. So if let's consider if in this case also it had not been able to separate the two classes, then we had to go into another dimension, extra dimension like n plus 4 two dimension because we have gone from n dimension here to n plus 1. So if this was not even separable in the n plus 1 dimension, then we had to go for n plus 2 dimension, but it was not the case. In n plus 1 dimension, we were able to get the required results. Okay, so we keeps on increasing the dimension unless the classes are separate. That we need to understand. So now let's come to the kernel tree that we have discussed in our machine learning PDF. So you could see that these values, this belongs to class green and these points will belongs to class dot I will call it. So you could see that we want to separate this green class from this dot class. So what we can do? So we have an x. So what will transformation I will go do is phi of x is x square I will do. So what happens is that so we get a parabola kind of thing. 2 square will become 4 here, here, minus 2 and plus 2, 4 will come here, and 4, 16 will come here, and minus 4, 16 will come. 16 here it will come, 6 will come, 36 come on, 36, 8 will come 8 is 64, 64 like that. So now we have drawn a boundary, decision boundary, hyperplane. Okay, so we have to able to draw a hyperplane which divides these two classes in such a way that we have got the unique classes, the unique values for each classes in such a way that green classes are in the one side and dot classes in the other side. As we can see here that the points were not linearly separable in one dimension, but after applying transformation, it became linear. So in this case, we have a dot class and yellow class. So this is easy. So we have 1, 2, 3, 4 kind of points just to export to over here. So whatever um, one reminder goes up and zero reminders come down. So now we were able to separate in a such a way that we have class yellow in the upper above the hyperplane and class dot in the down below, that is lower plane. Okay. So now what we have done till now in kernel trick is that when we have n dimension, we have done transformation technique and moved to n plus one dimension. Or if we had not been able to get the answer in even in n plus one dimension, we should have moved to n plus two dimension. This is what we have to do. So let me give a brief of kernel trick. So kernel trick allows us to operate in original dimension. So we have operated in the original dimension, okay, or feature space without computing the coordinates of our data in higher space. So we have not computed the coordinates of the data in higher space. We have operated in the original space itself using the transformation technique. So example of this is RBF, polynomial kernel, sigmoid kernel, and hyperbolic. So if I have to go to the previous PDF over here, there are different kernel functions available. Okay, Gaussian is RBF, that is radial basis function. Polynomial, when we are processing this, we will have to give the degree as well. For polynomial, so these are the different kernel functions available. Gaussian is radial basis function. Polynomial, when we are passing this, we'll have to give a degree as well. Then we have sigmoid, and then here we have ANOVA, and then we have base. Okay. So we will discuss this in the future classes. Okay, you don't have to worry about that. Now, next comes to the hyperparameters, that is hyperparameters of support vector machine. So in real time, the classes are not distinctly separated. There are some outliers. Yeah, right. I mean, you could see right in whenever you have a data set, there can be some outliers, okay, that cross hyperplane and enter the other classes as shown in the figure. So here what we have done is that we have tried to draw a hyperplane so that we are able to classify green and red classes properly. But what happened is that there are some outliers, like green classes has come here and red classes have gone there. So this is because in real-time data, the classes are not distinctly separated. Okay, there will be some outliers and that cross hyperplane and enter other classes. That's the main reason. Okay, so what we can do is that if we can allow some tolerance to outliers, if we give some tolerance to the outliers in the model, then the simple plane will be created. So this is the simple plane that we have created because we have given some tolerance for the outlier. So if it's green, let it be. Okay, it's red, let it be. There will be some outliers. I mean, we can't do in much anything. Okay. So what we have done is that we have given some tolerance. Okay. So what happens is that when you give some tolerance, the C value will be low. Okay. But the good thing is that the margin will be higher. Okay. Tolerance is also called regularization parameter. You need to understand the tolerance C is also called regularization parameter. Here, high margin can be obtained, hence also called high margin classifier. Since we have given some tolerance, there is a much huge advantage that we get a higher margin because we have allowed some tolerance, and here some tolerance will lead to low C value. So, okay, so this is how let's say, so this is the regularization parameter that we are going to discuss. So when you give this, you can see the red points over here and yellow points over here, sorry, blue points over here. So when we have drawn the hyperplane, you could see that the red plan has passed this hyperplane in the right hand side, and blue points have passed the hyperplane on the yellow side where red point should be. Okay, so you could see some outliers in the data set, right? So when you give some tolerance for outlier, then we have a low regularization, and that is low C value, low tolerance. Okay, then what happens is that we will have a higher margin. Okay, that's one advantage having a plane, that is when we allow some tolerance, then that there is advantage that we get a higher margin. Okay, that's what has happened in this case. So we have some tolerance for outlier, so low regularization. Let's see another case here. High margin can be obtained, also called high margin classifier in the low tolerance. So let's say in another case, we don't have any tolerance to outliers. We don't want outlier tolerance. it, what happens is that if we give no tolerance to outliers in the model, then complex problem plan will be created. This is the complex plan that we have created. In that case, the regularization parameter will be high, C tolerance will be high, no tolerance will be there. So here C value will be high. So here's margin will be too small. That's the problem here. If the margin need to be too small because we're trying to fit the complex pain so that we get no tolerance to outlier. So margin is too small over here. Okay, this is the problem. So here small margin is obtained, hence also called low margin classifiers. Okay, this is low regularization parameter with high margin. Whereas this case, when we are building a complex plane, then this is high regularization parameter with the low margin. Okay, so this is how it happens. So C is higher means model will choose a smaller margin classifier. C is low means model will choose a high margin classifier. So in example, if I have to say, so let me take gamma first. So gamma, so two key points to remember here in the another, like we have in the hyperparameters, the other parameter that we are going to discuss is gamma. In gamma, low gamma means consider farther points. High gamma means only nearby points. Let me discuss in brief, okay? Low gamma means far, high gamma means near. Imagine you have a data set with two classes and is separated by support vectors. We have two classes and it is separated by support vector. So here is a support vector and here is a support vector. If you are making the gamma high, it means that the model has to give more attention to nearby points. So if you have made the gamma high, gamma higher gamma, so it has to take care of the nearest point. So so it has to take care of these nearest points. It will look at these nearest points and it will see that there is two rabbits over here on the hyperplane. Okay, so it will keep focus when high gamma is there. So low margin will be happening. Okay, this hyperplane moves to here. Here, this hyperplane moves from a position this to this, and we will have a very low margin. So just think uh, you have a hyperplane down over here because you have a high gamma. So what you are trying to consider is nearby points it will check. Okay, so you will draw hyperplane over here. You will draw support vector over here, and then you have another support vector. There is another hyperplane over here. So you will get a low margin, right? You understand, right? I mean, we get a low margin. From here, hyperplane, you have a so very near distance, and from here, so very near. So, if you are making gamma high, it means model has to give more attention. If you pass low gamma, it means the model will give attention to far. So if you pass low gamma, so further points it will consider, and it won't consider this. So what happens is that these two classes, rabbit classes, will be in the lions den, lions class. So it will be differentiated into lions class. So we have drawn hyperplane such a way that we get maximum margin as possible. As that's what we low gamma does. Low gamma gives higher margin, making sure that we have a high margin with which will give you a better result, but high gamma gives lower margin, which will look into nearby price. As low gamma gives high margin, we consider farther point. So this will consider farther points from here and farther points from here. Whereas high gamma will look into nearby points if it is there or not, which is the main problem or the cause that giving us the low margin. Okay. So this was all about the GAM support vector hyperparameters that we discussed. So these were the hyperparameters of support vector machine, that is gamma and C. Okay. Now moving to, so we have discussed hyperplane. So hyperplane is the plane that is distinct between support vector passing through passing a line passing in between the two support vector is hyperplane. Support vector is a support vector is a what do you say, a line passing through the first class and parallel to the second class, or we have line passing through the classes, okay, at the edge of the classes, okay, that we say support vector. And kernel trick, we have already seen kernel trick where we have radial based function and what else we have? So radial basis function, we have polynomial, we have and polynomial color, we have sigmoid kernel, we have so polynomial kernel is x square, let's say, and dimension sigmoid, and then we have after that we have ANOVA and Bessel, and then we have looked at what is the next concept really hyperparameters. So we have looked at C hyperparameter, that how we can do. So high C, where high value of C means low margin, that is high regularization, which is leads to low margin, and low C value means high margin, which is low regularization equal to, so model chooses high margin. And high C value means we don't allow out, like we are actually building. So high C value means we are building a complex plane, whereas low C value means we are building a plane which gives maximum margin. Okay, where outliers will be present in our classes. Okay, some outliers, some tolerance will be given, and zero tolerance will be given if we have high regularization. And gamma we have seen. So high gamma means only nearby points it will look, and the low gamma means it will consider farther points, and which is high margin. Okay. So then margin we have discussed high margin and low margin. So now let's discuss multi-class classification. So this was all about support vector machine. So I'm going to discuss about multi-class classification. So let's say we have three classes, class A, B, C. So how are we going to define the true positive? Let's say for class A, this is positive and this will be positive. Okay, actual and predicted positive. Okay, for let's say actual is positive and this will be negative for class A, and prediction will be like this is positive and this will be negative. So what will be the true positive? So true positive will be only A will be positive. So this will be cell 1. So true negative will be, so BC and BC are negative. So BC are negative here. So here BC are negative, 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 negative. So this is also negative. So it will come 5, 6, 8, 9 will be true negative. So this is positive and this is negative and this is negative. So what happens is that our prediction is negative and the actual is positive. So that will be true negative. Sorry, false negative. So false negative will be 2 and 3. And similarly, over here, our prediction is our prediction is positive, but our true actual value is negative. So negative, negative, but actually is positive. So false positive, 4 and 7. Similarly, when for class B, if you do multi-class classification, so this will be positive, so this will be positive, so 5 class will be positive. Cell 5 will be positive. So cell 5 will be true positive. When you consider true negative, or others will be negative, A, C, A, C negative. So when we consider true negative, it will be, so this is negative 1, 3, 7, 9 will be negative because negative, negative, negative. Now we have our B as negative and A is predicted positive. So what happens is that A is actually negative and B is predicted positive. Okay, so we will get false positive. So 2 and 8 will become false positive because predicted is negative, but actually is, so 2 and 8 will become, because predicted is negative, but actually is predicted is positive. Here also predicted positive, but actually is negative. So false positive will come 2 and 8. So when you can look at this and this, so actually is positive, but you predicted negative. Here also actually is negative, positive, but you predicted negative. So that will be false negative, which is 4 and 6 will be false negative. So the assignment will be try same for C as well. So the thing is that if you consider for C, true positive will become cell 9. Okay. So true negative will obviously become 1, 2, 4, 5. And false negative will be like this is positive and this is this is negative and predicted as positive, right? This is false positive. 3, 6 will be false positive and 7, 8 will be false negative for class. Now, this was your assignment. I have already told you. So now let's take label A, B, C. Okay. So now let me tell true positive as 3 for there are three true positive and false positive is 2 and false negative is 7. And B, let me say just it's a random values I'm taking. 1 true positive, 7 false positive, and 9 false negative. Similarly, C class will have 2 true positive, false negative 3, and 1 false negative. Okay, false positive 3 and 1 false negative. So precision is nothing but true positive by true positive plus false positive, which is 3 by 3 plus 2. This is 3 by 5 is 0.6. Similarly, precision for this is 1 by 8 is 0.12. 2 by 2 plus 3, 5.4. So precision for A, B, C classes we have got. And recall is nothing but 3 by 3 plus 7, 10.3, 1 by 1 plus 9.1, and 2 by 3.66. So we have got our precision and recall. So macro precision when you want. So then you have to add A, B, C classes to positive. 3 plus 1, 4, 4 plus 2, 6, 2 plus 7, 9, 9 plus 3, 12, 7 plus 9, 9, 16, 16 plus 1, 17. So you have to now calculate the macro precision. So macro precision is nothing but the 1 by third, that is there are three classes, 1 by total number of classes, 1 by 3 of precision, zero point 0.6, 0.1 to 0.4. So that one is your macro precision. And macro recall will be 1 by 3 of 0.3 plus 0.1 plus 0.6. So we have got our macro precision and macro recall. Now we want micro precision now. So micro precision is nothing but true positive total by true positive plus false positive. That is 6 by 6 plus 12. And micro recall is 2 positive by 2 positive plus false negative. That is 6 by 17. So we'll get some value. Okay. So these are macro precision, macro recall, micro precision, micro recall. So when you apply classification report, okay, from SQL and root metrics, when you import classification report, and when you apply that on the white test and white predictions, then you will get the macro precision and macro recalls, and also we'll get the weighted value. Okay, so how we get the weighted value, let me tell you. Okay, let's say for class A, B, C, the p value is 0.3. Okay, proportion, and zero point 0.4 and 0.5 respectively. Okay, so the support, let's say this has 300 support and zero point 0.4 has 100 support and zero point 0.5 has 600 support. So the proportion per weight is 300.3, 0.1 and zero point 0.6. How 0.3, 0.1, 0.6? 300 by 300 plus 100 plus 600. That is 0.3. So 100 by 100 plus 300 plus 600. 0.1. And 600 by 600 plus 100 plus 300. So that is 0.6. So this is the proportion or weight. Okay. So weighted precision. So this is the precision. Okay. So precision is 0.3, 0.4, 0.5. Okay, and the weighted precision is the proportion per weight that we calculated into zero point 0.3, the precision of A, plus proportion per weight into precision of B, plus proportion per weight into precision of C. So 0.3 into 0.3, 0.4 into 0.1, 0.5 into 0.6. So this is how we calculate weighted precision using support. Okay. So this was all about support vector machines and with multi-class classification. So today the class of multi-machine learning ends. I have covered all the algorithms in machine learning. So in the next sessions, I will be covering the case study for machine learning. Okay. So thank you so much for attending the session. But okay, let's wait. Actually, I have to cover coding part for support vector machine as well. So in the next session, I will cover that as well. The building of support model. We'll build a model, support vector machine model, and I think that will be the last class of machine learning. And after that, I will be going to take a class on case study. Any case studies I will take for machine learning. So thank you so much for attending the session. I hope you enjoyed the session.